Well, good morning, everyone. I'd like to get started this morning if we can. We've got an action-packed breakfast meeting this morning, so I want to make sure that we take the time to get through things. My name is Bruce McKellar. I work with Field Crops Pest Management down in the southwest part of the state. I cover a lot of issues kind of statewide, and so this morning, we want to make sure a couple things happen. Please mute yourself for all of our speakers in there during the presentations. Please sign in with your first name and last name. You can click on the participant list at the bottom of the screen and find your name and hover, and you can click more, then rename yourself in there. And that's important to do that so that we have the record for your RUP credits if that's what you'd like to do. You can ask questions in the chat box found at the bottom of the screen. And then the RUP and CCA codes will be given around 7:30 a.m. And my partner in crime, Phil, will make sure that we get that into the chat in there and some more instructions. So we'll remind you later in that process. MSU extension programs are open to all, and the collection of demographic data from program participants is an important and mandated aspect of all Michigan State University extension programming. This is voluntary, and the information that you provide will not be used in any way to identify you personally, but rather as a member of a group that participated in this program. The link has been shared in the chat. We ask that you take a moment and fill out the information so that we have a good idea about participation, and we can make sure that our programs fit everyone. So please do that if you can. I'm very pleased to introduce Dr. Bruno Basso today. Bruno is a person who has worked for MSU for a long time, looked at technology. He's a great outside-the-box thinker of everything agriculture. And so we're going to turn it over to Bruno, and he comes to us today from Rome. So he's been on travel for a little bit. So thanks, Bruno, for joining us this morning and sharing.
Thank you very much, Bruce, and thank you, Phil, for organizing this and inviting me to deliver this short talk about the work that I carry on with the Basso Lab. It's a pretty extensive group of talented and passionate students and staffs at MSU in the Department of Earth and Environmental Sciences and Kellogg Biological Station. I have this double appointment. I know it's very short, 15 minutes, but I'll do my best to deliver to you how we basically integrate suites of technologies with the ultimate goal of, reach sustainability in the sense, first of all, profitability while protecting the environment and as well as social acceptance. We have been exposed to digital agriculture for the last few years, but before that, agriculture is obviously not new to breakthroughs in innovation, starting from the beginning of the centuries with mechanization, following with agrochemicals, then biotechnologies, and digital information that is now mixing, data sciences, robotics, so lots of engineering. But as an agronomist, Bruce and Phil, we feel that agronomy plays a critical role in using technologies, because I always say it doesn't do any good to have a very precise, applicators if we don't know what to spray and with the amounts and so on. So we have witnessed use of drones. You'll see some of how we use them. We have a little fleet of drones, not just to monitor, but we're going in the direction of even apply inputs using drones, or nowadays some of the latest technologies be able to irrigate large-scale fields with robotics and small robots to at this stage still for phenotyping, getting information, but potentially there could be a revolution of a small fleet of robots to collect information. Certainly in small high cash crops, horticultural crops for sure. Extensive crop is more of a problem, but the extensive crops and intensively managed like corn and wheat and soybeans are the biggest user of this large scale application, because as we all know, they have a very thin margin from profits, and so anything that allows to reduce cost and expand the capacity of managing larger areas is beneficial. And so there is a large interest in understanding how we could use this technology. And I was pleased, and I thank Bruce for the comments, but I do think a little bit differently from a more, I would say, conventional type of application of a small scale, let's say, agronomy, because my interest is not just to help a single farmer, but large scale, agriculture. And so you'll see how my main question in agronomy has been, how do I scale technologies? And the reason we've been able to do what we're doing today is I was fortunate enough to have a large grant from the USDA, and we've been collecting a very large amount of data sets from farmers. These are not even updates. It's just a few months older, but we have in-house about 7,400 yield maps flown over images from all over the states, and so the possibility of analyzing spatial and temporal variation of high quality yield maps has allowed us to see things a little bit differently and be able to see that the integration of space and time really provides valuable insights, not just on the way things managed, but also the role of weather. And farmers seem to have, we came to a conclusion, a little bit of a short span memories. They always remember last year or maybe 2 years behind, and they always think that they're going to be alike. And we think that the historical analysis, as you'll see the yield map flipping here and the spatial variation being really predominant, is the norm rather than the exception. So by integrating all these geospatial data layers, both from yield maps or airborne, as you'll see in a minute, we came up with a concept that has been used for a long time now. But this flip-flop, we wanted to understand how each single piece or pixel or parcel or small areas is different from the neighbor, and how is it different over time. And so by looking at this, you basically be surprised but how much consistency there is in a field, in a sense that there are areas that they constantly produce high yields and areas that they constantly underperform, and then areas that are highly affected by the interaction of the system. Not just weather, because weather is the same across the field, but one year one area is flooded, and another year it gives you the highest yield. Same on the opposite end of the topography feature, where you have a hilltop which gives you high yield when you have a good rainfall distribution in a wet year, but it doesn't do well in a dry year. So this flip-flop allows us to understand what are the factors affecting unstable zones. How do we scale? We can't rely on having yield maps, and so we feel, what is the next thing that is able to look at the same time at the performance of a crop? And that's called remote sensing. We are doing a remotely sensed action right now. We're looking at the screen. Our sensor is the eye. Healthy plants absorbs it. We still see the plants green because of chlorophyll, but a darker green obviously shows healthy and rich in nitrogen. A more diluted and lighter green, it's a sign of deficiency. Same thing in the near-infrared, when they flip-flop from being a healthy plant high near-infrared or lower. And the interesting thing is that if you look at the numbers in the sensors of whether it's a drone with different sensors or a satellite, if you have high reflectance in the red, it means all the other compounds are covering chlorophyll, so carotenoid, xanthil. But if you see that in the middle of the season when things should be green, then you know that you got a problem, because it's either senescing early or you have signs of diseases or deficiency. So with the idea of using remote sensing, we came out with this breakthrough, and we were able to develop yield stability map for the entire Corn Belt. So in this case, we started with 70 million, 80 million, and we basically process this pretty much except Florida and some other states and California where the acreage is low. You can click on any field on a website and be able to get the exact field with the common land unit. And so with this analysis, we learned that you can see the percentage there. About close to 50% of the entire Midwest in fields have high productivity, 25 always low productivity, and 27% they fluctuate from being high yield 64% of the time and low yield 26% of the time. So this, if we did a mass balance in this paper and quantified all the impacts that this was in Nature Scientific report, and we quantified the amount of fertilizer that ends up in the Mississippi River, the amount of close to 600 million of unused fertilizer because of the inefficiency, the energy lost, and the CO2 emitted. So with this in mind, what else? How can we use this knowledge of spatial variation? And the knowledge of spatial variation, before we go into impact, it's also very important to understand the unstable zones, and this is done through a thermal stability map, which is a concept that I developed in the last couple of years in understanding water relation with plants. So you'll see the two areas where you see dark blue, that is cold and stable. It means plants are cooler and they're able, it's a proxy to understand that there is a deeper soil profile, enough water to be able to satisfy demand. Where you see yellow or red, they're hot and stable or unstable, they run out of water quickly. And they're pretty much mirror image of the performance of the plant. And with some work that we've been doing with George Bird in potatoes, we learned that the stability map is a very good proxy for soil health indicators, whether it's because of shallow soils and properties. But anyway, this is a critical novelty that is going to be useful for farmers to understand how to better manage their fields. And I mentioned that the unstable zones are affected either by water deficit or by excess water. And so this is actually part of a work that was funded by the GLISA consortium. And we analyzed this fluctuation of weather and the probability of obtaining water access or drought. And so you see as seasonal rainfall anomaly, as rainfall increases, the hilltops do well. As rainfall increases, the depression, lose yield. That's a common, concept. But the fact of quantifying it for the whole continental, U.S. Now we have about 3 million hectares, so about 7 to 8 million acres that they are affected by these unstable zones. So we know exactly where parts of the field are going to be water access versus water deficit. The use of the low and stable zone has been really important to us because, as shown again with all the losses, that despite the fact, this is an analysis that we did in Michigan for 67 fields where we analyzed the low stability zones, despite the fact that they had plenty of nitrogen, the yellow boxes there, you can see they constantly had lower yields, showing that these low and stable zones are not limited by nitrogen, but rather the possibility of using water to use nitrogen efficiently, and that's constantly over time. And so that's really the basis of the way we deliver prescription maps to farmers. So we integrate images from drones or airborne or satellites. This is an example of a variable array, and the impact that a farmer sees of not impacting yield in each of the zones by using more efficient use of fertilizer, by accounting for the yield stability zones, and using crop simulation models to analyze what if scenarios. What if I put 120? What if I put 140 pound? What is the probability of response, not just to 1 year, but on 30 years of weather? And so we know the distribution of the responses. And this work continues in quantifying, leaching, which is a student project, BJ. It's a student of Dr. Andreessen and I that is looking at using stability zones as an area where better management through, again, reduction of environmental impact can be quantified. Now, the last few slides are going to be important in a sense of the future work that we're doing. You all know that farmers are very interested in carbon farming nowadays. It's a possibility of obtaining additional income. So this is a novel piece of analysis that we're doing of converting the as-applied map of variable rate that we deliver to the farms. This comes exactly from the way it is from the applicator. And so the knowledge of reduction is converted into nitrogen saving. Now you have references from the high and stable zones versus how much lower nitrogen you put in the low and stable zones. And so nitrogen saving in the areas that they receive the normal amount, you save 0, but in some other areas you save 33, in this case is kilograms per hectare, which is similar to pound per acre. And so that's converted into CO2 equivalent and carbon credits. So we're working with producers to convert an as-applied map into a completely verifiable, without sampling or anything, completely verifying way of obtaining a demonstration of reduction of abatement of greenhouse gas emissions. This is one way of benefiting through the use of technology for sustainability. The other thing is we're introducing a novel concept of profit stability. When you have a yield stability, you have a knowledge of the yield, which changes with prices and so on. But the middle map right there, it shows the areas that over the last 7 years of corn, over a total of 11 years of yield data, the red areas have lost $200 per acre. Any farmers that sees that does not feel comfortable. And believe me, they're not familiar with these areas losing this much money. They barely know the amount of cost of production. They do have a thin margin, but it's still a way of living or a sufficient amount that, and also the complexity of getting into this level of analysis, but it's becoming much more available, and the goal is to make it simple. So to wrap up this, we use profit stability to quantifying basically introducing this new concept of precision conservation, where nitrogen is applied at the full amount, where you have a response and you need to continue to produce and getting high yields. But on the areas that we have quantified to be low and stable and losing money, they can get benefits in terms of incentives through the new programs, whether it's through the carbon banks or by incentivizing through basically reducing losses. And so to biodiversity, because you increase the benefits on the corn as well as the increasing soil carbon through roots of these perennial plants. And so we recently got an NRCS grant, one of those conservation innovation grants, but pretty large, of a few $1 million, to work with producers that they're willing to use these two technologies. Variable rate application of nitrogen through yield stability analysis and modeling, and dedicating the areas of unproductive land. So we know this is throughout the continent, the Midwest, let's say, or where the low and stable zones are. This is what it looks like when we do an analysis of a farm. All the areas in purple are the ones going to go into biodiversity conservation areas. And so they are converting this and receiving incentives. So this is the beginning of a new way of farmers be able to allocate these environmentally, vulnerable zones with something more sustainable through this technology that we could help them. So the analysis, I know it's hard to see a table like this, but if we were to manage in a sense of producing high yielding in the where nitrogen is response and converting the low and stable zones, whether they are located in the middle of the fields or on the edge of the field, we have a knowledge of how many pixels, how big are these areas of low and stable, from less than 1 acre, greater than 1 acre, how aggregated they are. And so this is going to be in a paper that we're working on. We could reduce almost the amount of 1.1 teragrams going into the Mississippi River. And to basically finish the story, that if we were to do precision conservation, the amount of carbons and benefits will be even greater. I know I went fast. I wanted to thank you for your attention, and obviously thank the funders that allow this research to take place, and all the people in the Basso lab. Thank you very much indeed.
Thank you, Bruno, for joining us this morning and presenting that. Bruno, I've got a quick question for you I wanted to get started at least with. And, you know, I'm an old farmer at heart, so my question is what's kind of the low-hanging fruit for technology that guys could use almost immediately, either hang on the boom of a sprayer or remote or whatever to improve kind of management of where we're at? I mean, looking at what's really causing problems in fields. Do you have any insight on that? What might work for us?
Yeah, that's certainly a good question, Bruce, because the majority of the farmers may not necessarily be on top of things in terms of technologies. You know, I would say if they they must have a GPS driven, you know, tractors and things that they can at least, you know, monitor, you know, the fields. So it actually, Digital Ag started that way. You know, the adoption of GPS mounted on tractor is close, you know, in the 90% or 95% is a technology that work. And farmers are using technologies when they have an immediate benefit. And they will continue to do that because the advantage will be not overspraying or not missing, you know, areas where they don't put. The next step is, it has been historically, the knowledge of yield variability. And I have taken that layer one step further by saying, okay, you know, this is a yield map and no one really has capitalized on. People may think, yeah, but every year is different. That's exactly the point. And if it is different, you'll be surprised which part is different and which part is never different. And so immediately, whether they can contact us to, you know, basically help them explain and how they could get to their own yield normalization or yield stability. I mean, the softwares that they often use provide I would say a similar way, but they don't give you the insights about unstable, so what's driving the changes. So in a nutshell, the knowledge of yields and the immediate conversion into cost, and you know, you get this much from this field and you have spent this much, it's already good enough to raise red flags, because the yield stability analysis, the profit stability that I've shown, I would challenge, and I guess there is a question from, you know, Mr. Leon Cook there that I'd like to answer if you've seen it in the chat. It's it doesn't make sense that a farmer loses $200 on those areas, and that's not just because of the profitability aspect, but also because it's inefficient from an environmental standpoint. So the answer, Bruce, is really trying to pay attention to areas that they constantly do well and regard that areas with a common management, you know, manage for the good season, for the good areas. But in areas that they have been, take a little bit of courage of lowering the input, because it has shown that continue to do what you've been doing, it didn't do any good. You continue to lose that money. So that's with low tech, without having, you know, observation about areas that they don't perform. And so it actually connects to the question of Leon. If you want me to connect this, you know, the maps of the fields look like something that the government could use to force us to do things they want. Well, first of all, you're not in Europe. Europe, they force you to do things. In the US, they reward people to do things. And I think a farmer will never be imposed. It is changing that you could be incentivized. If you have a knowledge, and that's what science is going in that direction, if they help you analyze in areas, it's like very much like medicine. If you know that you have a problem in your body, why continue to ignore it when you now have a possibility of providing a solution with it? Now, the solution has to be paid. I mean, that has to pay off, has to be rewarding to the farmers. No one would like to see corn be removed. But if the argument is, if your corn is 140 bushels, you know that you're not getting the money worth. You spending a lot more, an average of 550 or so in Michigan versus less than 500 or 450. It doesn't build the cases. So I wouldn't be worried about the government imposing things, but it's the way of incentivize a new way of agriculture, which is basically allowing the soil to be better and building soil carbon, allowing roots to be more in a perennial phase, be there, and the possibility of growing cover crops. I obviously could not touch here, but you could allocate low productivity crops to producing cover crops for seeds. Everyone wants to use cover crops in the rotations and so on. And only, basically 15% of the Midwest is under cover crops. Also because there are no seeds of basically scaling 80 million if everyone wants to do a cover crop. So there are different ways of managing the fields that they are. What we've shown is this is a good area and you should invest in, getting the highest yield. This is not as good of an area and you should be courageous enough to reduce the input.
Bruno, there's another quick question in there from one of my colleagues from St. Joe County, and he's asking, Eric Anderson, is there a generalized recommendation for consistently low-yielding areas? In other words, he's like increased or decreased seeding rates or inputs to increase productivity.
Yes, that's also very good, Eric. Yes, there is a pretty good rule of thumb that the low and stable zones should receive less input starting from the seeds. I mean, the fact that you have a crowded area that just competes and uses nitrogen, so a reduction of low seeding rate on those low and stable zones, it's obviously the way. You wouldn't go the other way around because you'll have really thin crop and not having the cob to be filled all the way. Green filling will be affected because during the time of transfer of water and nutrients during the critical stage, the soil is shallow, doesn't have the resources to, basically fill the grains. And so low seeding rates is one. And even if you don't want to go all the way to be, with the precision conservation, reducing nitrogen to the uptake of, if you're producing 140, 150, your nitrogen should not be 150, or it should be significantly less. And you see a benefit from anything that it's again from the environment as well as from the reduction of the cost. So profitability, remember, can be obtained also by reducing cost, because sometimes those yields can never be greater on those areas because of limited the way, the hilltops or the shallow soils. The question from Phil, how does variable rate programs? Okay, well, that's also very good, and we face that question all the time. We have even had a grant to compare the different variable rate application from commercial, from Bayer, from Corteva, and the others. Our approach, we don't compete in a sense that we are on the farmer's side, because we are the ones for the taxpayers to produce, actually bring a little bit of justice to the commercial world. And we don't have anything to sell. So if it comes from a seed company, the last thing they want is to basically impact that. And so, long story short, the variable rate maps are very different. They say, don't you dare to lower your nitrogen. My seeds are really good. And you can never have a low yield blaming that you didn't put enough nitrogen and now my seeds are no longer as good as you think they were. So the rationale behind is totally different. Now they're changing because, as you may know, Nutrient, for example, pays money to farmers for carbon credits while they sell fertilizer to them. So they said, don't worry about use fertilizer. We're going to compensate the emissions from fertilizer. And so the industry has a mandate. I mean, they sell depending on who's providing those variable rate maps. Now, from a technical standpoint, some Bayer, for example, give the rate based on yield potential. Okay, good luck in knowing what yield potential is spatially in an areas where you don't know. So the farmers has to get that input that very uncertain. My point is going to be different from another's, and so there isn't a consistency. They give you shape files where you would go and change the rates, but you put the rate. So disclaimer off, like no nitrogen, you do that. But they still disclaim of putting low nitrogen in. The other are, for example, remote sensing companies. It says it basically gives the same thing. It gives the shape files, the spatial variability through remote sensing, but you put the rates. The rates of other companies are based on the potential, but they don't give you the spatial. And so if you gather what we produced is that the yield stability is the integrator of allowing the plants to tell you what has happened under very broad conditions of weather. And so the fact that, and we have published this extensively, the fact that the best, it's like nowcast, Jeff, of weather. What's the best predictor of weather? Nowcast. You look and it's similar condition from before. If you go further ahead, you lose, credibility. The best predictor of yield is history of yield, the historical yields. So once you observe that you have a stable yield, that's the predominant of that. Those yields are going to be in that direction. Unless you have learned through this analysis what's unstable. And that's what our benefit through this GLISA project and others is to show farmers what are the areas of instability. And so the yield maps, rather than worrying that looks like, something, it's actually helping you of saying, are you on the low, in a depression, is a wet year, or there are lots of proxy as the season goes by that we basically can help farmers in manage these unstable zones. So it's quite different, but yield stability in a nutshell, it doesn't includes the history that they don't use in the commercial world. Would the maps help me understand whether improved soil drainage? Yes, very much so, because first of all, you learn the probability of having flooding in your particular field, given the weather. It's, 2 years out of 10. It's becoming now 4 years out of 10. And we have actually a study where with producers, they have shared us drainage maps, and there is quite a bit of an investment because of the memory span. Wet years, the next year, they bought machine to put drainage. And we showed the benefit from the yield maps realistically, but also through simulation. So if you don't have anoxia, if you don't lose heterogeneity of the stands, number one variables of yields, it's like if instead of you plant 9 plants, per square meter, in the end you end up with 4 because it was flooded. And so all those things can be quantified, but you can't do a trial and error because you will never you always chase the type of weather. So that can only be simulated. And this comes again with this level of technology that we call more now like more of a digital twin. Before you do this, you can simulate this impact. And that's where the research is going. And we're trying to make everything here, basically available to the farmers publicly. And also talking to the government to be able to make all this technology in a way that farmers receive incentives rather than worrying about not to, hide about the nitrogen they use or so I think it's a really good time to be in agriculture, but it's because in addition to the grains, finally farmers can be rewarded to manage the land the way they're doing it, but they also have to play a little role in being proactive in joining the fact that they can do profit by using less input. What's your thought about biological production of an in-grass crop? Organic, you mean? Organic production? So manure management, I guess. Could you expand? Am I understanding right the question, Bruce?
That's a good question. I'm just curious.
So if you say biological, I can tell you right away, manure is very, very important. It's critical. It builds long-term. It does not satisfy the immediate needs of a crop. And so if you have a knowledge of the decomposition and the mineralization, then it's important to know weather conditions and how much nitrogen is released. All this information pretty much available. So, biological or again, organic, it's very good from an environmental standpoint in a sense, but it's not the solution, because we have shown actually that manure continues to release nitrogen when plants do not need as much. And so you could potentially have leaching losses of nitrogen from a completely organic system. You can have green manure like through cover crops. That it's also a tricky business because it immobilizes carbon. You return carbon and the carbon immobilizes nitrogen. So as you know, in no-tillage, you may have to prime it a little bit at the beginning. If you have a long-term no-tillage with lots of residues, it may tie nitrogen up because of the CN ratio that, soils and plants maintain. And so all these things are not novel, but we're going towards more solution-based, and it's a combination of knowing the system and the weather, but it's not just one solution that you go manure and you save your environmental problem. The reason we have mineral nitrogen is to satisfy the plant's need immediately when the plants need it. On the roots is more like the new technology of pivot bio or cooler fertilizer, and yes, that's certainly a promising technology. As you may know, we work closely. Actually, one of my postdocs was recently hired by them, and it doesn't release the full amount what the crops need. It's in the range about 20 to 25 kilograms, and it would be beneficial. It's still 25 kgs of less emissions in terms of greenhouse gas emissions, and it's slow released and on the roots. The problem that they shared with me is spatial variability, that in some parts they don't do as well as others. So there's a still knowledge gap there. But remember, you supplying 25 kg. So you could reduce your application if you use a biological like pivot bio. That's certainly the way they're selling the products. But there are actually no large-scale data sets to be able to show the complete benefits. They have kind of sporadic trials, and they're going bigger on that. Anything else?
Just one quick comment. As I'm sitting here at home on the farm, Bruno, and watching 4 deer running across the field here, we almost need your fleet of drones to run them off, I guess.
That's right. Yeah.
Variability caused by browsing and stuff in there too. I know data is so finding the right root causes of why we have that variability can be kind of an issue too. And I suspect that since those patterns do show up year after year, they could probably be part of that yield stability portion, right?
Bruce, that's a good question. We're looking into that. And through both literature, we haven't really collected data, but we have shown two things that are rewarding for us to understand. Yes, the wild life damage on the crop is in the range of 20% reduction. And that mainly occurs on the edge of the field. It's a general, but it's pretty good rule of thumbs, okay? The thing is that the yields are not 20% less than the rest of the fields. The other thing is that we have shown, in order to do a difference and says, okay, they can eat the corn once it comes up. But when we monitor the crop is stented already from the beginning. So because of, low emergent, and the reason at least on the edges of the field, is a combination of basically shading from trees.
Sure.
Heterogeneity of the stands, they're not uniform. The headlands are managed differently. There is compaction. Most of the traffic occurs. So it's a combination. Now, if we were to have only one every other year, the low and stable are never unstable. They're low and stable, and they tend to be about, we quantify about 30 to 40% of the low and stable is on the edge. And so how is that problem solved? By having first, could be a bait of, like few areas. I mean, some corn growing as, how do you call it? Yeah, right. But then the rest of a thick biodiversity native, it could really basically not allow them to go through. But the damage is not to the ones that justify not removing the crops, because the losses are much greater the benefits, especially if the farmers, we succeed in giving incentives for biodiversity, to having these bioconservation areas on the low productivity areas, they will be in the range of basically the cash rent. So we heard from a farmer, which I loved and I repeat, it says, when you rent a land, it's like the barbecue. You get the meat and the bones. We're trying to not have them paid for the bones. So actually get only the meat when you rent, and the bones will be paid by the government to incentives to build better soil health, perennial through the roots, and get this system. It's a mini CRP. We got a new grant and we want to show actually how much carbon has been built over, CRP, but we push to have subfield CRP and getting paid for that. Now it's not, necessarily allowed. And so it's really a combination. The key message here is, the good areas, they need to produce and you can manage and you don't lose money on those areas. But the one that you're losing money, I challenge why continue to do that when there are alternatives.
Fantastic. Thanks, Bruno, so much for all the information and taking time out of your busy schedule over in Rome to be able to be with us this morning. Safe trip home for you, and looking forward to seeing you soon. For the rest of us, join us again next week for our virtual breakfast program, and we'll learn a little bit more about what's going on at KBS. So, Phil, I'm going to turn it back to you.
With that, I'm going to say thanks, everyone. We'll see you next week.